Hello guys, and welcome to another calculus video. I know it has been quite a while since I've been making videos, but I've been kind of focused on studying for other things. So anyway, let's go ahead and jump right into this really fun problem. We have the integral from 0 to infinity of x over 1 plus x squared times inverse tangent of hyperbolic cosecant of pi x over 2, which clearly looks like quite a fun problem to go ahead and take on. We're going to jump right into it. And my method for solving this is pretty unorthodox, and it's a pretty interesting method in my opinion, but I get to use a very fun result from a past video that I have in here. So we have actually a lot of formulas that we're going to need to be using. The first formula right here is from a past video, which I will go ahead and link as a card in the top right corner. The integral from 0 to infinity of natural log of 1 plus x squared over t squared all over cosh of t dt equals 2 pi times the natural logarithm of gamma of x over 2 pi plus 3/4 times gamma of 1/4 over x over 2 pi plus 1/4 times gamma of 3/4. Then we're going to be using the Dirichlet beta function. Beta of s equals the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 to the s power. And using the derived value, which we are not going to be deriving in this video, but you can go ahead and find a proof online that beta prime of 1 equals pi over 4 times gamma minus natural log of pi plus pi times natural log of gamma of 3/4. Let's go ahead and jump right into the integral. So the first thing we're going to try and notice here is we're going to try and unpack this inverse tangent of hyperbolic cosecant of pi x over 2. And I can tell you that the person who wrote this integral definitely put this hyperbolic cosecant in there for a reason, and I'm going to show you why that is. Notice that if we take hyperbolic cosecant of pi x over 2, this is 2 over pi x over 2, e to the pi x over 2 minus e to the negative pi x over 2. Now if we multiply by e to the negative pi x over 2 on the top and bottom, we actually get 2 e to the negative pi x over 2 over 1 minus e to the negative pi x. And this is actually, interestingly enough, if you know the formula for the tangent angle addition formula, tangent of 2 theta equals 2, or tangent of 2x equals 2x over 1 minus x squared, which is actually exactly what we need right here. We just have, in this case, our x is e to the negative pi x over 2. So what we're going to do is we're going to let e to the negative pi x over 2 equal tangent of theta. Then that means that hyperbolic cosecant of pi x over 2, which is this expression right here, actually equals tangent of 2 theta, which is pretty interesting. So this means that tangent inverse of hyperbolic cosecant of pi x over 2 is actually 2 theta, which means that it's 2 times tangent inverse of e to the negative pi x over 2. Now that was a little bit involved, but essentially all we're doing is manipulating this expression right here and realizing that this is actually, this hyperbolic cosecant is just sort of a way of giving us an angle addition formula. So this actually transforms our original integral to 2 times the integral from 0 to infinity of x over 1 plus x squared times tangent inverse of e to the negative x dx. Now we can go ahead and integrate by parts. We're going to be integrating natural log of 1 plus x squared and differentiating inverse tangent of e to the negative x. Now at infinity, this inverse tangent term dominates, and at 0, this term goes to 0, so both of these will go ahead and disappear. Then we can go ahead and substitute everything in, and we get pi over 2. Notice I put e to the negative x here. This should actually say e to the negative pi x over 2. Sorry, that's a little bit of a typo, but I fixed it over here where we get pi over 2 times the integral from 0 to infinity of natural log of 1 plus x squared over pi x, so e to the pi x over 2 plus e to the negative pi x over 2 dx. Now we can go ahead and rewrite this as pi over 4 natural log 1 plus x squared over cosh of pi x over 2 dx. And this is looking a lot like our original formula that we had at the beginning, but we do have to do a little bit of manipulation to go ahead and get it into the right form. So we have 1/2, after doing u equals pi x over 2, we're going to get 1/2 the integral from 0 to infinity of natural log of 1 plus 4 over pi squared times u squared over cosh of u du. We're going to go ahead and split this into 3 separate integrals. So first of all, we're going to take out this u squared from everywhere, and we're going to just completely move that outside of the integral. Next, we're going to take out this 4 over pi squared, which is actually 2 over pi all squared, and we're also going to take that completely out of the integral, and we're going to be left over with this other term. So essentially, we get all this split up. We take out natural log of u squared is the same as times 1/2 is the same as natural log of u. Natural log of 4 over pi squared times 1/2 is the same as natural log 2 over pi. And for this last term, we still have this 1/2 in front. So now we have these three separate integrals to evaluate. They're all pretty straightforward, but I'll go ahead and walk you through them. So for I1, we have this natural log on top, and whenever we have a natural log, we can think of replacing this with a Mellin transform and then taking the derivative of the Mellin transform. So for the Mellin transform of hyperbolic secant of x, which is the same as 1 over cosh of x, we're going to get the integral from 0 to infinity of x to the s minus 1 over cosh of x dx, and this is the same as 2 times the integral from 0 to infinity of x to the s minus 1 times e to the negative x over 1 plus e to the negative 2x. Now we're going to go ahead and expand 1 over 1 minus 1 plus e to the negative 2x as an infinite series, which can allow us to evaluate this integral term by term. So we get 2 times the sum from n equals 0 to infinity of negative 1 to the n times this integral right here. After doing v equals 2n plus 1x, we find that this can be expressed as a simple gamma function right here. So this is just going to be gamma of s, and then we're multiplying by the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 to the s, which is just the beta function, Dirichlet beta function right here. Now when we go ahead and differentiate this Mellin transform, we just get a product rule expression right here. And this differentiating this right here, which is the same as the Mellin transform, we find that we're going to get x to the s minus 1 times ln x over cosh of x dx. Now, if we go ahead and plug in s equals 1 into all of this, we're going to get our original integral right here, ln u over cosh of u. And so plugging in everything, gamma prime of 1 is negative gamma, beta of 1 is just the sum of, what did I just do here? Sum of negative 1 to the n over 2n plus 1 to the 1 power is just a very famous series that evaluates to pi over 4. And then we have this really complex expression for beta prime of 1 that we're just going to substitute straight in. This gives us our value of I1. For I2, it's going to be a much simpler situation. We're just going to go ahead and multiply by e to the x on the top and bottom and factor out all our constants. So we're going to get 2 natural log of 2 over pi, integral from 0 to infinity of e to the x over e to the 2x plus 1. And this is actually just the derivative of inverse tangent of e to the x. So we can just go ahead and evaluate that in two places, and we get our final answer of pi over 2 ln 2 over pi, which is pretty interesting. I mean, pi over 2 ln 2 over pi, I think it looks pretty nice. Then for our last integral, we're literally going to plug in into our formula from the beginning. Just plug in pi over 2 for our value of x, and then we're going to get 1/2, so we end up with a pi out front, and then we get gamma of 1, gamma of 1/4 over gamma of 1/2 times gamma of 3/4. Quite a very interesting situation, and actually we're going to see a little bit of simplification when we add together I1, I2, and I3. We get a ton of natural log of gamma functions, and it actually turns pretty nasty, but after you go ahead and simplify everything out, I won't walk you through all the boring stuff we have to do here, but multiplying gamma of 1/4 and gamma of 3/4 together several times, and we actually are going to get something that has a very nice result, which is pi times natural log 2 over square root pi. What a nice result from a very cool integral. Again, thank you to Elmonious for posting this integral in my Discord channel. It was a lot of fun to solve, and I was really glad that I was able to use one of my past formulas for this. So thanks so much for watching. If you watched all the way through, I hope you enjoyed the integral. Feel free to leave some suggestions for integrals in my comments or on my Discord server, and I hope to see you next time. Thanks, and bye.